Alright, welcome back to Meteorology 101. In this video, I'm just going to go over the satellite radar, look at this current weather system in the central U.S. Looks like a low pressure system, an occluded low, and a cold front extending all the way down off the east coast of Texas. Looks like some pretty significant, maybe convection off of right over Louisiana. And we're going to pull up some weather charts and pull up some other isolated radar areas and see about do some cross sections, see how severe this stuff is, how far in the upper level it goes to, and maybe look at the severe outlook. So right now I'm seeing a low pressure system. I'm saying an occluded low because you have this wraparound. This would be a cold occlusion. So the cold front will come out of the middle of that low. If you see the rotation of this low pressure system, let's place that just based on satellite. Let's get a good look at this thing right around northeast Kansas and northern Missouri. So low circulation right there. If you can see my mouse. There it is. So low circulation right here. A cold front, or more of an occluded front. An occlusion is where the cold air undercuts the warm air and they become overlapped. So it reads as an occlusion on a surface chart. A cold occlusion is when cold air catches up with the warm air. Warm occlusion is when warm air overrides the cold air. So this is more, I would say, a cold occlusion because of the shape of it. The occluded front would come out of the low pressure system, wrap around, tie into the cold front, and just keep on going to the south. And right along that area of clouds, you got the perfect comma system right here. Now the warm front, if you replace the warm front, you'd bring that occlusion out, bring it around, and then your warm front would typically kind of come out to the east, but I'm really kind of not seeing that right now. We'll put up a radar, see what's going on. Looks a little bit drier in the central areas. So maybe with that high pressure system that just moved off to the east coast, maybe creating a little bit of a blocking pattern. Sometimes you'll get that high pressure sits there, won't move out of the way. The warm low pressure system can't move it out of the way. So that warm front kind of drops down and kind of right along the head of the cold front. So you'll get that blocking pattern going on. It's kind of seems to be what's going on right here. With the high pressure system, if we were pushing onshore flow, warm moist air, that would give us all the lift we needed right over top of that cold front. The cold front causing a lift, so you got moisture, instability, and lift. So you have all the recipe for convection in that area. Right into the occlusion, same thing with that front, though. You have that cold occlusion pushing through, creating like a dry line, almost like the dry line you'd get in Texas in Tornado Alley when that acts as a cold front and creates that lift. Sometimes you'll get like an inversion holding everything down, and then all of a sudden that inversion breaks and it just pops, and then you get explosive thunderstorms with possible supercells tornadoes in that area. Now this one would be kind of the same thing with the dry area squeezing up into that occlusion. You can see all that dryness act like a dry line. You can see a little bit of cloud buildup in northern Illinois, but closer to that low pressure center is where I would look for any major convection. Say right there in northern Missouri. That would be the where I place that. Now it looks like we have a low pressure system, pretty significant rotation right off the east coast. So we'll have to see if that's a low pressure system out there. And then I see two different directions over the west coast, pretty much over the four corners. Almost looks like if you have to place this jet, it could be kind of a long wave trough from the jet stream. You can see that pushing south. Those clouds are pushing south and then wrapping around and pushing north. So you have a long wave trough over the four corners. And then that's going to cause all the instability you need right up over that mountain range. That's going to pretty much cause any snow or rain, depending on the freezing levels in the over the mountains. So, like I said, I see that rotation there. A little bit of a tail hanging out. And over Mexico, then that blow off cirrus from the jet stream. I see that jet stream comes up, goes back down, wraps around, and creating a ridge, and then blowing off over that ridge. Some blow off cirrus over the Great Lakes region. But it looks like some low clouds wrap around moisture off this low pressure system, creating some onshore flow in the lower levels. Blow off cirrus above that, but you got in the low levels, you got the onshore flow and creating a little bit of instability over the Carolina, North Carolina, and Virginia. All right, so let's get to the radar. Look at we'll go to national radar first. So we can definitely see our rotation right around there, right around northern Missouri. And then you can see the areas of heavier rain, possibly some convection. And then some definite areas of heavy rain over Louisiana, Mississippi, Alabama, the southeast there. And then that break in the that dryness right over Kentucky. So once we pull up that surface chart, let's see what kind of features we got going on there causing that. And then, like I said, the rotation around the Four Corners area, and it's just this widespread scatter of rain and snow all in that area. So we'll pull up these surface charts, see what's going on here in a few minutes. So looking at the rotation, you can see that's your perfect. I mean, this has that break in there, but that is a pretty textbook comma system. Baroclinic low, wrap around. The only thing we need to look at is, this frontal system, how far on the upper levels the low pressure system extends. Does it stack? Is it upper level supported by upper level troughs? I would say it obviously has jet support, so it is a pretty significant system. But if that's a low pressure that's going to deepen into the upper levels, how severe this stuff can get. So we need to take a look at that before you start calling out severe weather. Now, severe weather, it really doesn't take a lot to create a severe thunderstorm. So severe thunderstorm warnings can pop up at any time. Anytime there's a thunderstorm, it's just it does not take a whole lot of atmospheric dynamics to become severe. When you get into the tornadoes, the heavier convection, say like down here along Louisiana, you get in that stronger, heavier rains, you're creating a strong enough downdraft, that would get wrapped around any support that of an updraft to create any tornadoes. I mean, you're getting into the red areas down off the coast, so real common to have water spouts all along the Gulf of Mexico, right along the coast. All right, so let's continue with the radar. Let's get some local radars pulled up. Here's one for Iowa, northern Missouri. Play that loop. So you can see that this is pushing to the north because it's got that wraparound. That's where that low pressure system is. So a little bit of convection there. Let's go over to another radar real quick and let's see what we have. Let's do a cross section. Really not anything significant there. What I'm looking for is 50 dBZs. You're right around 39, 49, close to 50, and the lower levels right around maybe 5,000 feet, 6,000 feet. But you start pushing 50 dBZs at 10,000 feet or higher, then that's where you'll start, start to get a little concerned about severe weather. Look at the velocity. Really nothing going on there either. Upper levels, 5,000 feet or so, you're about 49 knots. So like I said, really nothing severe just yet that I'm seeing. So if we get one of these cells that builds up, we can do a 3D shot of this thing. We could pull up all the precip on this. You're not even looking at that. Let me go over here. There you go. Now we got a 3D shot. And that's all pretty weak reflectivity. We could drop that out and pull it to the little bit brighter blues, higher reflectivities going into the green. Now you're getting into your a little bit heavier precipitation, and then we should start seeing yellows. And then if there's anything really significant, we might see a red or an orange. So I see a little bit of orange there. Nothing much. So right there. That's about 5,000 feet. That's weak. So nothing really to brag about here. So we do have that low pressure system wrapping around. Let's go pull. Let's go to the south. I'm going to see. Let me get rid of that. That's all base reflectivity. Let's get over here to another radar. Okay. Go down to Louisiana. We got Arkansas. We've got some flash flood warnings going on down there. See if Lake Charles is back up. Well, we got a little bit of rotation here, so H8. You can't see the pop-ups. The depth is 15,000 feet. Base is at 8,000 feet. Low-level divergence. Let's see, we got two of these cells. Max relative velocity 43 knots, height 10,000 feet on the upper, on that northern part, and then the lower rotation, area rotation, height 10,000 feet. Max relative velocity is 41 knots. So we can start seeing some severe weather to the south as this thing builds up. Let's download the loop. Let's watch the loop real quick. This is along that frontal system. They had a warning over to the east of us. So flash flooding. Okay, that one was severe thunderstorm warning for southeastern Baldwin County. And that is now canceled. Pull up Mobile radar. Definitely had a lot of rotation going on there. Let's go back to our 3D radar. Now let's drop down to those areas, see what we got going on. Okay, Mobile. Go download the loop. It's a base reflectivity. Alright, so now we can see some stronger stuff off the coast. We do have that warning. And that is a special marine warning, coastal waters, Pensacola, Florida. And strong thunderstorms capable of producing water spouts were located along the line of extended to 10 nautical miles south of the Gulf shores. Alright, so let's pull a 3D shot of this thing. Alright, you can see that one. Let's get this up. That's pretty weak too. I do have the color shot out, taken out of that, so we can build that back up. We do have the green precipitation. You can see once you get up into the yellows, oranges, reds, you got a little bit of red there. So that would be not quite 10,000 feet, almost there, but really, really small areas. So nothing just yet. I mean, you could always have a water spout. There's so low friction over the water that water spout can pop up pretty easy from that. So we get up into the Gulf Coast over Pensacola. We could do a cross section on these two. Get you over here. All right. There's the cross section on that one, and that is pushing 50 dBZs. Still just under 10,000 feet, so we're just not quite there on the severe weather yet. With the sun going down, diurnal cooling, that's going to make it a little bit harder, but you do have that frontal system continue to lift. You have the instability, so the diurnal cooling is going to weaken it a little bit, but it's not going to put it out. So all right, let's go get some charts real quick, and we can try to see what's going on with these systems. Alright, so surface chart, sea level pressure, low and highs. We do have the high pressure system over southern Missouri. These charts get a little extreme on this stuff. Probably got some pretty strong ridging right there, but nothing. I wouldn't say. Let's pull up the surface plots and we can see if we have any actual rotation right there. We've had a pressure gradient that tight, you'd have some pretty strong winds over Illinois. We got some 20 knot winds over Missouri, so 10 knot winds, 20 knot winds. We'd have some 25 knot winds from the northwest, just south of that low. So this low pressure system's pushed over to the east just a little bit, and then we do have the warm air advection to the north, causing steady rain, IFR conditions. All the blues, marginal IFR, where sailings are between 1,000 and 3,000 feet, or visibility's between 3 and 5 miles. Red is the IFR, that's sailings below 1,000 feet, and or visibility below a mile. So we do have the southerly flow along the coast, reporting thunderstorms, onshore flow, about 15 knots. So it's a pretty good onshore flow there. And if we look at our rotation, we do see around this low, definite rotation around that low pressure system, 20 to 25 knots. That is pretty significant there. The high pressure system, I don't see the wind shifting off. I don't see that westerly flow to say, hey, there is a high pressure system there. I could say, yeah, there's some ridging in that area, but that's what's pretty much causing that occlusion to dry out. That area we seen in the radar, that was just a dry area. That's the high pressure suppressing all that moisture. So breaking up right there and then reforming down to the south along the coast, and we have the onshore flow giving us all the moisture we need. So that's the surface pressure chart. Now we have the low pressure system, kind of, this chart's kind of putting these two together, but that low pressure over the Four Corners area, we can see some rotation there. And if you look at temperatures, let's go back over here to, I can throw fronts on here, the computer generated fronts. I'd much rather draw them, but that takes so much time. I try to keep these videos fairly short. But we can throw fronts on here. We're going to see probably an occlusion come out of that low. Right there, it throws that low pressure system to the a little bit further south. Throws an occlusion on there, coming down into the cold front, and that cold front actually would be stretching out, connecting to this cold front and stretching out further to the west. And then there's the high pressure system with that to the north, causing that damming that pushes that warm front down to the south, and then any onshore flow pushing up over that area, that warm air advection pushing up over that ridging, then that's causing your lift for those thunderstorms. So that's your frontal system. Then the computer just throws a bunch of stationary fronts around here and there. Now there's that low pressure system off the east coast of North Carolina with some troughing. And then it's showing kind of an occlusion there, but it's wrapped up pretty good. So there was some pretty significant rotation there, and then the onshore flow, and causing marginal VFR conditions over in that area. Now we can pull a stability chart for potential severe thunderstorms. And these are pretty much real time. These aren't forecasts, or they're actual conditions that are happening right now. So if we see any severe weather, we should probably see it along the Gulf Coast. I don't have the National Weather Services pulled up yet for their severe weather. I think theirs was in the same area, but then pushing all the way up to Iowa, and then to northern Missouri. They had a pretty significant area right there. I can push this algorithm a little bit stronger, and we can go. It goes overkill sometimes, so I don't like to use it a whole lot. But we can. I do have another one here that's. Let me see what we got. It gets pretty bright on the colors for the red, so there's your strongest point right there, and then it does push all the way up into Iowa, and then actually all the way up into Lake Michigan area that has another area. This is like an advection chart. It shows instability, so being on the east side of that Lake Michigan, could just be picking up something there, for like the way winds blowing across Lake Michigan, and then like lake effect snow would happen or something. But it's not saying lake effect snow. It's just saying that the advection that's happening on that side of the lake could cause severe weather, which is probably a little slim at this point. I would push more along this frontal system, that low pressure system that's over western Missouri, northern Kansas, northeast Kansas. I would say that would be the places I would look for more for the severe weather potentials. Okay, so we know we had the low pressure system over northeast Kansas into Missouri. If we go to the 850, we could build the height. There's a closed low over the southwest United States. Then we have ridging over that area of Missouri, and then troughing to the west. So pretty significant ridging. A little bit of troughing actually over from the Ohio Valley all the way down into Arkansas. So with that, associated with that low pressure system, there's a trough that could definitely cause some upper level instability, then and help us out with that severe weather in those areas. If we pull up the temperature, we can see that a lot of this is barotropic, so that gets pretty weak over here on the west side of that ridge. The east side of that ridge. On the west side of that ridge, you do have some cold air, warm air advection pushing up. So it is baroclinic on the back side of that ridge. So at a trough and ahead of the trough, at the ridge, behind the ridge, where you're going to have the most instability. So this should be pushing off to the east, and then once that deepens that low, then which being a ridge right above that low pressure system, it's going to kind of cap it off. So I wouldn't expect this thing to explode too much. If anything, I would look for if the frontal system to the south, but this is all pretty barotropic too, so I really don't see a whole lot happening down there. Especially your diurnal cooling at night, you're going to be that's going to weaken that whole scenario for us down there. So pushing for any tornadoes, I'd say probably slim. We'll see what tomorrow brings once the sun comes back up, and then get into a little bit more more significant instability, then look for that stuff to fire back up. Deepen that low, and then create that thing, cause that thing to create a little bit more significant weather in the central U.S. 700 millibar. Still that ridging, pretty significant, pretty strong troughing. We're getting into some pretty strong troughing. I say over the four corners, like I said, with that jet stream, it looked like that jet stream. We were getting that northerly flow that was coming down and then wrapping around and then becoming southerly. So we were looking like we were getting that upper level low. We maybe possibly a cutoff low in that area. So when we're looking at that satellite, we're seeing that rotation. That was a pretty sharp area of rotation. So I'll definitely say that's starting to become an upper level low. We'll have to see how that develops. Sometimes, like if it's just a cutoff low, they'll hang around the four corners area and then just dissipate out. What we look for on that is to the west, pull these charts to the west, and we can see like if there's a major short wave that comes along, it can kick that low pressure system out of there. Then that's when that can become a well-developed system once it gets on the lee side of the mountains and then push out and then cause all kind of weather all through the eastern United States from that. So, but a lot of the times they just sit there over the four corners and just cause the on and off rain showers for days until they just fill and then finally just dissipate. And it's just on and off rain showers for days over in that southwest United States there. So we got, let's go to 500 real quick. We'll pull a vorticity chart. First we'll do the 500 millibar. I still have that low pressure system ridging over the central U.S. Throw some temperature. We could throw some plots on here. The upper air plots. That's what all this data is extrapolated from on the computer models. It's not even a model. It's actual real time. So the charts actually, this program takes that data and analyzes that data for constant heights based on those weather balloons that they let loose. So all this black is significant moisture, the dew point depression. That dew point depression is the difference between the temperature and the dew point. So if it's a 5 or less, if it's just a 5-degree difference or less, then you have saturation and you have significant moisture at these levels. So we do have significant moisture over Missouri, Kansas, all through that central U.S. over the plains that is all the way up to 500 millibars, about 18,000 feet. So that is pretty significant too. Something to keep an eye on. So let's go run a vorticity chart. The vorticity chart is going to show us upper level divergence, areas of upper level divergence, and then we can compare that to that frontal system and that low pressure system and see what kind of how significant this thing really is. I mean, so this is not impressive at all. Over the four corners, we have some pretty strong positive vorticity, but over that low pressure system over Kansas, Missouri, that's all negative vorticity there. We have a little bit of a area of positive vorticity advection, pretty weak over Oklahoma, northeast Oklahoma, but there's over North Carolina and Virginia, that's where our strongest vorticity is. I mean, that's still kind of weak, is that this computer's it's pushing it pretty good through there, but we did have that low pressure system off the coast and we have that instability right there. So I would agree with that one because of the there's all that cloud cover we were getting over Virginia and North Carolina. This is pretty weak. The only thing we have going for us on this is that low pressure system over northern Missouri with the occluded low in the frontal boundary pushing to the south, and then any high pressure pushing onshore flow, pushing the warm moist air over that frontal boundary and causing any instability there. That's it. I mean, any significant upper level divergence, rotation, it's pretty weak here. So let's go with let's go pull a jet stream real quick. Like I said, I'm not impressed with this system at all. So I do like the radar and the satellite. It's textbook, picture perfect, but it's just not a real deep low pressure system that's just expanded to the upper levels. I like to see I like to see closed lows going all the way up into the upper levels. That's when you can say you got a pretty significant system. And then once you start getting that convection, then you have the upper level divergence. You have really the buoyancy. Once that air partial rises, it hits a level of free convection, and there's nothing to stop it. So, that there's closed low pressure stacked all the way up in the upper levels. That is actually what gives you that level of free convection. You can just, once a thunderstorm pops up, it's gone. Now our jet stream, we can see a bunch of fingers of the jet. We need to put some streamlines on here, see which way this is going. We got the jet max coming out of the northwest, pushing down, and then either pushing down and then wrapping around, trying to create that cutoff low. And then we do have that ridge over the central U.S. and then ridging back up and then pushing back around to the southeast. So trying to create that cutoff low, but maybe it's just going to try to shoot over to this one, but I don't know if that's actually going to happen. It's pretty deep there, but it's pretty weak also. Let me get the station plots on here. So there's the pressure on here first. See what our heights are at. And like I said, we see that ridging. Got the troughing over the Four Corners area, then just kind of throwing a low pressure system to the south a little bit. Weak temperature advection. There's at 250 millibars. It's about 34,000 feet. So we do have significant moisture over that low pressure system right there. Kansas, maybe northern Missouri, Nebraska. We do have moisture all the way into the upper levels. Right along the panhandle of Florida and the northern parts of Florida, we have some significant moisture in the upper levels all the way up there too. So we do have the moisture that we need. Now these winds are just all over the place. Trying to point out where the jet stream is, that's pretty rough. Let's do a couple things real quick. Let's throw a streamlines on here. Let's see where our jet stream's flowing. Alright, so we do have that little bit of troughing. And then it's just kind of a little bit of weak ridging with the way the jet is flowing. So we know our flow is from west to east. It's always west to east, but a little bit of ridging there, and then a little bit of troughing off the east coast. So that's our overall flow pattern. Now let's get rid of that, and let me see if I can get something else going on here. Get you guys the display, and let me see if I can draw something. Let me look at these, trace these wind patterns out, and kind of see what we got going on. See if you can see that. Okay, let's just try to see what's going on. These wind patterns are, like I said, are all over the place. So do we have any closed lows in the upper levels? I don't see anything. We've got this ridging, so it's really not like a closed low going on here. So we got winds going out this way, out this way. So I mean, that's some upper level divergence right there, just the way the direction is. It's diffluence. We got some confluence going on here right behind it, and diffluence. So our winds are kind of pushing around that way, kind of push it around this way. I guess the wind's coming down through here. have to stay behind that one, but almost like a area of confluence here. Almost be like diffluence there. So I mean by diffluence, confluence, winds are coming together on a confluence or convergence, and then winds are going apart on diffluence or divergence. So when you're looking for the areas of divergence in the upper levels like this, you start drawing out this pattern. I mean, typically if you get something like, I'm trying to see what this pattern is going to do. You can get a pattern like this, then you can get the confluence, diffluence, and then so now I'm going to erase that for a second. We definitely got the diffluence there. So it'll be upper level divergence in this area. That's where we're looking at all that weather to be possibly severe. So that makes sense. Now, there's two different types of convergence and divergence too. It's directional divergence and speed divergence. So here's one. We got about 90 knots right here. 65 knots there. So you got more wind going in than you do coming out. So you're going to have speed convergence. So that wind's piling up right there. So that's going to force that wind down because it can't go anywhere else. If you're up on 250 millibars, you're up about 34,000 feet. Once you start hitting that tropopause, the winds they're going to try to spread out because it's catching up with that wind. You do have some wind shear, significant wind shear right there. And then it's going to start kind of a downward motion right there. So, but actually, if you looked at that where we had that radar, we did have that break in that radar in that area, so that kind of makes sense. Got more wind going in than you do coming out. There's a 50 knot, there's a 90 knot. So right there, that high pressure that was on the surface, that's what we're looking for. That's why we're seeing that that dry area. You got convergence in the upper levels pushing down, and then that's just suppressing that moisture. So 90, 75, 80 to 90. So we got speed divergence right there. And then we got that diffluence. So like I said, you can definitely see that we have this area, instability, and possibly there's really not enough data right here to tell, but possibly a little bit of, we do have 70 knots right there, 60 knots right there, so you got more going in than coming out. So that's going to kind of weaken that just a little bit right there. So I would put that more, any instability to the east of that. So I just stuff to look for the small details on the charts for the data. If you have the data that's there, enough data on the charts to point that out. Now we know coming out of Jetmax, there's 100 knots, and then there's 120, 115 knots right there. So you're another 115. So that's showing 100. So your Jetmax actually extends all the way a little bit further south than what this chart is showing there. So. All right, let's go back to the radar and the satellite real quick just to look at it. And because like I said, that satellite is picture perfect on that low pressure, that comma, all the way down. That is a textbook low pressure system with the comma, well developed in the lower levels. So if this was extending low pressure, closed lows all the way up in the upper levels, I'd be a little more concerned about this storm. But this thing's just it's pretty well developed. I like it on the surface, so I'm not knocking it at all. But I wish it would be up in the upper levels a little bit further. Same thing with that radar. Like I said, we got that that line to the south, we can keep an eye on that. I mean, you do have the moisture, the instability, the lift. You got everything you need for thunderstorms. You'll probably see some more severe thunderstorms down in this area pushing through, because with that area of advection, of vorticity advection stuff, that would be, I would point most of your severe weather along the Gulf Coast. So, all right, I'm going to end this video here, and I want to say thanks for watching. If you like what you see, if you learn anything, hit the like button, subscribe to the channel, and share. Help me get this out, and we'll keep these videos coming.